Welcome. In this lesson, we will explore the crucial role of mechanical work in HVAC systems. Compressors, pumps, and fans are key components that drive system performance by enabling fluid movement and heat exchange. Understanding the efficiency of these elements is essential for designing energy efficiency HVAC systems. We will also discuss thermodynamic limits on performance, which define the theoretical efficiency boundaries for this system. By learning how to assess and optimize efficiency, HVAC professionals can reduce energy consumption, lower costs, and improve overall system sustainability. Let's begin. In this lesson, we will cover the fundamental thermodynamic laws that govern HVAC systems and the properties of substances such as air and refrigerants. We will talk about conservation of mass and energy and thermodynamic properties of substances. These foundational concepts allow us to analyze HVAC operation effectively. By the end of this lesson, you will be able to explain how HVAC components perform mechanical work, assess system efficiency using key performance metrics, and apply thermodynamic principles to optimize HVAC operation. These skills will help you design more energy efficient and cost-effective HVAC solutions. I want you to reflect on the next. Imagine that you are responsible for improving an existing HVAC system in a large commercial building. What specific upgrades or modifications would you consider to enhance efficiency and reduce energy consumption? Upgrading an HVAC system requires strategic decision making. Will you consider adding a variable speed drive, improving insulation, or integrating smart controls? Each of these modifications can enhance efficiency and reduce energy waste. Understanding how mechanical work and efficiency interact in HVAC systems will help us make informed decisions about system upgrades. Work and energy relations in HVAC. Mechanical work is a critical function in HVAC systems, enabling fluid movement and heat exchange. Compressors raise refrigerant pressure to facilitate cooling, while pumps transport fluids through the system and fans recirculate air for ventilation and temperature control. The efficiency of these components is measured using isentropic efficiency, which compares actual performance to an idealized scenario with no losses. A higher isentropic efficiency indicates a more effective component with minimal energy waste. For a device requiring work such as a compressor, the isentropic efficiency is the ratio to the isentropic to the actual power. For a work output device such as a turbine, the isentropic efficiency is the ratio of the actual power to the maximum possible or isentropic power, and is defined as this. Similarly, the coefficient of performance (COP) is used in refrigeration applications to assess how efficiently heat is transferred relative to the energy consumed by the system. COP is then defined as the ratio of the heat flow rates into the system, the desired refrigeration effect, divided by the net power input. The limited performance of a cooling cycle is the Carnot refrigeration cycle, which can be expressed as a function of the source and, the sink temperatures only. Using absolute powers, the COP for cooling is expressed as this. So optimizing the work-energy relationship in HVAC systems involves selecting high-efficient components, reducing pressure losses, and controlling system variables such as airflow and refrigerant flow rates. Implementing these strategies ensures lower energy consumption and improves sustainability. Thermodynamic limits on performance. The second law of thermodynamics dictates that no system can operate with 100% efficiency due to unavoidable losses. In HVAC applications, these inefficiencies arise from heat transfer limitations, fluid friction, and the mechanical losses in moving components. Isentropic efficiency is a key metric for evaluating how compressors and pumps deviate from from ideal performance. A system with higher isentropic efficiency requires less energy input to achieve the same output, making it more desirable from an energy saving perspective. Similarly, while theoretical COP values suggest high efficiency, real-world conditions such as temperature fluctuations, component inefficiencies, and pressure losses reduce actual performance. Engineers must account for these factors and when designing and optimizing HVAC systems, ensuring that they function as efficiently as possible under practical operating conditions. In summary, this lesson highlighted the importance of mechanical work in HVAC applications, emphasizing the role of compressors, pumps, and fans. We explored how isentropic efficiency and COP serve as essential performance metrics, helping engineers assess and improve system operations. Additionally, we discussed thermodynamic limits that set fundamental constraints on efficiency. By understanding those concepts, we will improve our knowledge on HVAC. Now, for the next lessons, we will dive into the principles of fluid flow in HVAC systems, focusing on pressure drops, energy losses, and airflow management. Understanding these factors will further enhance our ability to design efficient HVAC systems. Stay tuned for more insights on optimizing airflow and reducing system inefficiencies. Thank you for listening to this lesson.